Combinatorial logic circuits form the basics of all of the computational devices that you interact with on a daily basis. So everything from the microcontroller on your Arduino all the way up to your smartphone or computer. And the circuits are formed by a bunch of logic gates that we'll go into in this lecture. So this happens to be one example of a logic gate right here. This happens to be a NAND gate, and we'll describe that NAND gate more completely. And logic circuits also have inputs and outputs. So in this case, for this particular logic circuit, we have three inputs. We have A, B, and C for carry, because this is in fact an adding circuit. This is going to add two binary numbers together. And the outputs of this circuit are going to be S for the sum and C for the carry out. Now, logic circuits like the one you just saw and logic functions in general are going to be described by truth tables. So truth tables are going to be an exhaustive listing of all of the possible inputs for that circuit. And these are binary inputs, remember, of all possible inputs, as well as the resulting output from that particular logic circuit. So a truth table is going to describe the behavior of a logic gate or a logic circuit, or any kind of logic function for that matter. Now if we go to the previous example and we want to describe the truth table for that example, remember we had three inputs, in this case A, B, and our carry in. And as outputs, we had the sum S and a carry out. And this was doing binary arithmetic, remember. So if I'm looking at an exhaustive listing of all of the possible inputs, I have three different inputs. Each of those has a possibility of being a 0 or 1. So two different possibilities. So 2 to the 3 will give me 8 combinations of these inputs. And so I'm going to write all of those out. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Alright, remember this is an arithmetic circuit, an adding circuit. So 0 plus 0 plus 0 is going to give me 0. 0 plus 0 plus 1 gives me 1, and I don't need to carry anything. Same here, 1, 0. In this case, 0 plus 1 is 2. So I get a 0 and I carry a 1 because this is binary output, remember? 1, 0, 0, same thing as earlier. 1, 0, 1, I get that 2 again. Same here, and 1 plus 1 will give me 3. So I'm going to have 1 as my sum output, and I have to carry a 1 here. Now we have a number of logic gates that can be used to implement a logic circuit or a logic function. I'm going to start with the easiest one, which is a NOT gate. This one is also called an inverter. And the symbol for this gate is going to be a triangle with a circle after it. It has one input. Usually we start our inputs for logic circuits and logic gates at the beginning of the alphabet, and we start our outputs at the end of the alphabet. So we're going to have A as an input, Z as an output. The truth table for an inverter is fairly simple because I only have one input. So I only have two possible, that's my exhaustive listing of inputs here, and it does exactly what it says. It's inverting, so instead of a 0, I'm going to get a 1 at the output. Instead of a 1 at the input, I'm going to get a 0 at the output. And the notation, if I write this out mathematically, if I write a whole logic function or a logic circuit out mathematically, I'm going to require some notation to do that. So inversion is often written as a bar over the letter. It can also be written as a prime after it. So this is saying Z is not A, or Z is not A. Same thing. One of the things that's important to realize is that that symbol that I just drew of an inverter, this triangle with a circle after it, is an abstraction. Right? What you encountered in 350 and what you will encounter again in 351 is if I'm drawing out the schematic, in this case of a digital logic circuit, I'll draw symbols like this. Now if I actually want to implement this in the lab or the real world in general, I might go buy an IC. A 7404 is an inverter IC, And that typically comes as a big package like this. It has a number of different pins on it. I'll just draw a couple to give you the basic example here. Maybe I have one here, but I have a bunch of different pins depending on the size of the IC. Maybe I have VDD up here, maybe I have ground down here, and I'll have a number of inverters in here. So typically these are drawn kind of like this. So I might have multiple, sometimes I have 6 inverters in a package, and so this would be labeled, for example, A1 and Z1, so that's the first inverter, A2 and Z2 right there. So if I'm actually implementing my circuit, my DigitalLogic circuit, in the lab, I would have to connect that VDD pin to some positive supply, say 5 volts, the ground pin to ground, and then I would feed my A into one of these sides and Z into the other side. And ultimately, as I mentioned earlier, these are forming the basics behind every computational device that you use in general, so microcontrollers to smartphones, and ultimately these inverters in those cases are made out of transistors. So the gate that you have over here is also made out of these transistors, in this case a PMOS transistor and an NMOS transistor together to form an inverter. There's my A as my input, my Z as my output, and I also have power and ground here. So if I'm actually making this integrated circuit, all I need are these 2 transistors. And as we talk about getting transistors down to the size of tens of nanometers, you can start to imagine how I can get a lot of different logic gates in a very small bit of silicon. An inverter is just one example of a logic gate. We also have AND gates, and this looks a bit like a truncated oval. I can have a variety of different numbers of inputs, typically 2 to 4. In this case, I'm drawing 2 inputs. My truth table, in this case, has 2 inputs, 1 output. And I have 2 inputs, 2 different possibilities for each, so I'm going to have 4 different inputs for my exhaustive listing. And this is an AND functionality. So if I think of a logical AND, if I have a false and a false, I'm going to get a false at the output. If I have a false and a true, I'm still going to get false at the output because I'm only going to get true for an AND functionality if both examples are true. So in this last case here. The notation for an AND looks something like a multiplication. So I write it as AB, or I can even write it as AB. And is often referred to as a logic multiplication. And you can see that in the truth table over here as well, right? If I add 0 and 0, I'm going to get 0. If I multiply 0 and 1, I'm going to get 0. 1 times 0 is going to be 0, and I only get 1 when I have both 1s here. I also have an OR logic gate. In this case, it looks fairly similar, but I have this curve at the front. I'm also going to draw 2 inputs here, but I can have a number of different inputs. And my truth table, in this case, is going to describe the functionality of this OR gate. I write out all of my different combinations of inputs here. And in this case, it's serving more as a logic addition. So I only get 0 in the case where both inputs are false, and I'll get 1s otherwise. And the notation reflects that. In this case, Z is written as A plus B. The plus in this case is our logical addition, or our OR functionality. And an OR are something that you've probably encountered in a particularly sophisticated Google search before, but one of the ones you probably haven't encountered is an XOR, or in this case it's also called an exclusive OR. In this case the gate looks something like this. It looks like an OR, but it has an extra line out front. I'm going to draw 2 inputs again. And my truth table here is going to be a little different from the truth table in the AND case. In this case, I'm only going to get a 1 at the output if my inputs are different. So in this case, my inputs are the same, so I'm going to get a 0. In the 1 and 1 case, my inputs are also the same, and I'm going to get a 0. And I get 1s here. So this row right here is really the difference between the XOR and the OR that we just saw. The notation for this shows that it is fairly similar to an OR, but in this case I have a circle around the plus side, and this is my XOR functionality right there. I also have another class of gates that are effectively the inverted versions of what we already discussed. So we have NANDs and NORs. The logic circuit that you saw previously, which was a summer, was composed entirely of NAND gates, and these become attractive because I can create particular logic circuits entirely out of a single base unit. In that case, it was a NAND. The NAND here, the symbol for a NAND, looks a lot like an AND, but in this case has a little circle after it, indicating the kind of inverter function. The truth table for my NAND is going to look like an inverted version of the AND. So if I write out all of my different combinations of inputs, for an AND, remember we had 0, 0, 0, 1. For a NAND, we're going to have the inverse of that. So 1, 1, 1, 0. And the notation for this is a combination of two notations that we've already discussed. I would have my AND here, and then I just invert it. So I could also do this as a combination logic circuit, as an AND with an inverter after it, and I would get the same exact functionality. Right? And this is where that notation comes from, but we make NAND gates separately from having to do this, and so this just makes everything a little bit easier. And then finally we have a NOR gate. So it's going to behave a lot like the NAND in that it's an inverted version of an OR. We have A and B as inputs, Z is my output. My truth table, once again, I have my two inputs, my single output, 0, 0, 0, 1, 1, 0, 1, 1. For the OR functionality, I had 0, 1, 1, 1. So now I'm going to have 1, 0, 0, 0. And my notation will reflect that same thing. I have A or B, that whole thing inverted.